So if we wanted to, you can just add up the number of atomic orbitals that went into making the hybrids, and that tells you how many hybrid orbitals there are. So since it's an sp2, okay, that uses 3 atomic orbitals. So we have an sp2 that uses an s and 2 p orbitals. Well, that's 3 atomic orbitals. I'm just going to call those AOs. Well, if I put 3 atomic orbitals into making hybrids, how many hybrid orbitals do I have to get out? Got to get 3. So I got to have 3 hybrid orbitals out. So if I put 3 atomic orbitals in, I have to get 3 hybrid orbitals out. Okay, and those things always have to equal. Okay, so an sp2 tells me that there's 3 because I've used an s and 2 p's. It tells me the recipe for the hybrid orbitals. So if I use 3 atomic orbitals, I have to make 3 hybrid orbitals. So the answer there is 3. The other way you could do it is to go through and do the dot structure for CO3 2 minus. And doing that, you would see that there's 3 regions where bonds are, 3 electron groups. And if you got 3 electron groups, it means you need 3 hybrid orbitals. So you have 3 hybrid orbitals there as well. So either way, you get the same answer. Okay, questions at all? If I had an sp3d2 hybrid orbitals, how many would there be? 6, because it's an s, 3 p's for 4, and 2 d's, that makes 6. Okay, so you just add up the total number of atomic orbitals, and that's how many hybrid orbitals you're going to get out. Okay. Let's see, number 2. Yeah. Yes. So number 2 says which orbital hybridization is associated with a tetrahedral charge cloud arrangement. Now, charge cloud just means electron groups around there. So if I have something, we'll just use something like a carbon, and let's say we're just going to do something like methane. It's a tetrahedral molecule. We know tetrahedron has 4 electron groups around it. And if I have 4 electron groups, that means I need 4 hybrid orbitals. So if I need 4 hybrid orbitals, how many atomic orbitals do I need? 4. And so you always start with the s. And then how many p's do I need? 3. And that's as many as we have, as you only have 3 p orbitals. But that leaves me with 4 atomic orbitals. So sp3 gives me 4 atomic orbitals, so that will give me the 4 hybrid orbitals that I need. Okay, so those always have to go together. I really hesitated writing down 4 Ho's because that just doesn't look right. Don't tell me you didn't notice that, because I just don't believe it. So, number 3. Yes? Yep, okay. So a triple bond is generally composed of what? So this is all valence bond theory. So if we have a triple bond, in valence bond theory, if we just have like two atoms that are going to form a triple bond, we use an example like these 2 carbons here in acetylene. Well, they form a hybrid orbital here and a hybrid orbital here. It's an sp2. And then they form a hybrid here and a hybrid here to match their 2 electron groups. And so these 2 hybrids overlap in a sigma interaction. Okay, so that's my sigma bond. Okay, because those hybrid orbitals are pointing end to end. Hybrid orbitals always form sigma bonds. And then we've got 2 unhybridized p orbitals on here. So we've got 2 that hook up like that, and so they can overlap this way. I don't know how this is going to come out in the diagram here. And then we've got 2 that are 90 degrees to that one. And so those are going to overlap that way. Okay, so we have 2 different pi interactions. So we have the sigmas that are pointing right at each other like this. And then on those carbons, there's 2 p orbitals that aren't hybridized. And so they're going to overlap like this. They're going to overlap like where my fists are, where my elbows are. So that's 1 pi. And then there's a 90-degree p to that one as well. And that's going to overlap as a p interaction as well. So an easy way of looking at it is anytime you have just a sigma bond, it's a sigma interaction. If you have a single bond, it's a sigma. If you have a double bond, it's a sigma and a pi. If you have a triple bond, it's a sigma and 2 pi's. And in Valence bond theory, it's always like that. Okay? It's a little bit different in molecular orbital theory, so don't apply that to molecular orbital theory. But in Valence bond theory, that's how it's always going to go. Okay? All right. Questions on that one? Everybody okay? Number 4. Okay, so for number 4, we're looking at the carbon-oxygen double bond in COCl2, and it can be described as what? So for that one, we need to do the dot structure for COCl2, and I'm just going to write it out so you can see what it looks like. I'm not going to go through all the steps to do it. But it looks like that. Okay, so what hybridization do I have on the carbon there? Remember, so your hybridization is always just that central atom. What's that? That's the shape, it is trigonoplanar. What's the hybridization going to be? How many electron groups? 3. So I need 3 hybrid orbitals, so that's going to be sp2. Okay, so 3 electron groups. So I know that that's going to be sp2 because that gives me 3 hybrid orbitals. So those are going to go along where all the bonds are. It's going to make a single bond in all of those places. Now we have 3 p orbitals on the carbon atom. There's 3 p orbitals on all the atoms there in the p shell. So we have 1 p orbital that's not hybridized. Okay, so because we only used 2 of the p's, we didn't use that third one, so it's kind of sticking up like that, if you want to think of it that way. And on the oxygen, that also has p orbitals, and so that can overlap there. Okay, so again, a double bond in valence bond theory is always a sigma bond and a pi bond. So the sigma bonds form from the sp2, they always form from the hybrids, and then your pi bonds always form with unhybridized p orbitals. Okay, so your pi bonds form from unhybridized p orbitals. So that's why the answer there is B. B. I haven't really been talking about what the answer is. You guys have the keys, so you can see what that is. Everybody good? Okay, number 5. Yes? Okay. We're going to do them all tonight, aren't we? Yep. All right. It is what it is. That's why we do these. So for number 5, so we're looking for the hybridization on the nitrogen atom in NO2 minus and NO3 minus. So in order to figure out what hybridization you have to go through and do the dot structures. And so we're going to do that. So for NO2, you end up with something like this. And for NO3, you end up with something like this. Okay, if you don't remember how to do dot structures, I really advise you go back to the Unit 2 material and do a little review there, because you've got to know how to do the dot structures in order to do this. Okay, so we want to count up electron groups. How many electron groups in that NO2 minus around that nitrogen? There's 3. There's 2 bonding groups and a lone pair. So I have 3 electron groups, which means I need 3 hybrid orbitals. So what's that going to be? sp2. Boy, sp2 seems to be the theme tonight, doesn't it? How about this guy over here? How many electron groups are on that nitrogen? Also 3. 3 bonding groups. Remember, that double bond is still just one group. So we have 3 electron groups, which means I need 3 hybrid orbitals. So also sp2. Also sp2. Questions on that? Questions on that? Feels like forever ago we did those, doesn't it? That was number 5. How about number 6? All right. I think Dr. Grumstrup said, yeah, I didn't have to do number 6. Number 7. You guys go 7? All right. So what's that? Do it? All right. Thought I was going to get away without doing that one. Okay, it's number 7. So if we're adding an electron into H2, it's going to go into what? Okay, well, let's look at the molecular orbital diagram here. Okay, so we got a 1s there and a 1s there. This is a hydrogen atom here, and we've got H2 right there. We've got our sigma 1s and our sigma 1s star there. Okay, so if we look at hydrogens, hydrogens both have 1 electron. Okay, now we're going to take those 2 electrons, we're going to put them into a molecule. Okay, so they're both going to go down here into the sigma 1s. So it forms just a sigma bond. That's all it is. If you do a bond order calculation, you get a bond order of 1 because you have 2 minus 0 over 2. 2 electrons in bonding, no electrons in anti-bonding. So you have 2 over 2, so you get a bond order of 1. If we add an electron to H2, where's it going to go? Well, it can't go into the sigma 1s because that's full. It only holds 2 electrons. And so it would have to go in up here in the sigma 1s star. Well, now that you're occupying an anti-bonding, just like it says, anti-bonding, yeah, they don't like bonding. So they start to weaken the bonding interaction. And if you do a bond order calculation on this, you now have 2 electrons in bonding, 1 electron in the anti-bonding, so you have 2 minus 1 over 2. So your bond order is now 1/2, which is less than 1. So you've weakened the bond there. So that's why the answer there is B. It goes into a sigma star molecular orbital, and that will weaken the hydrogen-hydrogen bond. Questions on that one at all? It's very much a thought type question. Number 8. You guys pretty good at filling those in. So number 8, you'll notice, and I had a couple people ask me this during office hours the last couple of days. So this one goes, the diagram that was given here went all the way down to the sigma 1s. Diagram that you're given on the exam just goes down to the 2s and just uses valence. None of the calculations change, just changes which electrons you need to use. If your MO diagram goes all the way down to the sigma 1s, well, then you've got to use all the electrons, the core electrons included, all the electrons, not just valence. Since we're doing our MO diagram starting at the sigma 2s, those are going to start at the valence. So we only need countervalence electrons. Okay, so you just need to make sure which one you're doing and where, but it doesn't affect your answer if you use the right number of electrons. You'll always get the same bond order or whatever. All right, number 9. You guys feeling pretty good with those? Just filling those in? I think last week's lab helped with that. Was there a yes? Oh, okay. So I got to do it after all. Okay. I'm going to have to draw that MO diagram. I'll draw it way over here on the side. So we want to use that MO diagram to determine which of the following are paramagnetic. Okay, so let me get in my diagram here and put in a 1s there, or 2s rather. And then we've got our 2p here. 2p or not 2p? That is the question on a cold night. Oh, that usually gets more laughs than that. My wife's probably at home rolling her eyes and she has no idea why. It's that psychic connection. We've been together almost 30 years. All right. So we can see that one okay. Not a very good diagram, I'm sorry. So we want to know which of these are paramagnetic. 8 and 9 actually use the exact same species there, B2. But we'll just kind of go along because it looks like these increase in number of electrons, I think. So for B2, 2+, since we're only using valence electrons, B2 is going to have, a boron has 3 electrons total. Okay, so we're going to do 2 there and 1 there, 2 there and 1 there. So we've got 6 total electrons in a B2. However, 2 of those are removed in B2, 2+. So we're only going to put in 4 electrons. So we put in 4 electrons for B2, 2+. We see that they're all paired. And because they're all paired, it's diamagnetic. Okay, so it's not B2, 2+. If we go to B2, well, now we have all 6 electrons, and so I've got to put the next 2 electrons in, and they're going to go in like that. Okay, because they follow Hund's rule there, where they don't pair until you have to pair. So the next electron will get paired up. But with this one, we see that we've got those 2 unpaired electrons in the molecule. Remember, your molecule is in the middle, and it's your atoms that are on the side. Okay, so the MO diagram for the molecule is right in the middle there. You see that we've got 2 unpaired electrons for B2. So that's our answer there, B2. If we are to go to C2, 2-, okay, well, carbon normally has 4 electrons. I'm going to go ahead and do the rest of these. So carbon has 4 electrons, and so with 2-, it got an additional 2. And so those would actually fill up that, and then fill up that. Okay, so that would be 10 electrons there. So we've got 10 there. N2, 2+. N2 normally has 5 electrons. Okay, so that would give me a total of 10 electrons. But then the 2+ would give me 8 electrons, and so it would just be these lower 8. Everything is still paired there. And then B2, 2-, I can't add that one in. So B2, 2- would have 6 electrons for B2 and would have 8 electrons for B2, 2-, and so that's going to be these 8, 2, 4, 6, 8, and everything again would be paired there. Okay? So that's why it's just B2, because we've got those 2 lone electrons there. Questions at all on that one? Okay. Change pages over here. All right. Number 10. Yeah, 10's kind of a weird one. So it says, given that O2 is paramagnetic and has a bond order of 2, and its highest occupied molecular orbital is anti-bonding, what would be expected for the bond orders of O2, 2- and O2, 2+? Okay. So if we look at O2, we can draw out our molecular orbital diagram, and again, I apologize, it's just not going to look very nice. So there's my 2s. My 2p, sigma 2s, sigma star 2s. Oh, this isn't going to look good. There's our sigma 2p, pi 2p, pi 2p star, sigma 2p star. Okay, so oxygen normally has 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've got 12 electrons we've got to put in there. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there's our oxygen. Okay, we see that it's paramagnetic. If we do a bond order calculation, we notice that we've got 8 electrons in bonding, and 4 electrons in antibonding. Okay, so we're going to have 8 electrons in bonding minus 4 electrons in antibonding over 2 gives me a bond order of 2. Okay, so now if we do what the problem says, if we go to O2, 2 minus. So if I add 2 electrons, where are those going to go? They're going to go into antibonding, aren't they? Okay, all my bondings are filled. I gotta add up here. So if I add into antibonding, I'm going to have 2 more antibonding electrons. So I would have 8 minus 6 over 2. Okay, so for O2, 2 minus, I get 8 minus 6 over 2 for the bond order, and that comes out to be 1. Now, if I go to O2, 2 plus, where do those electrons come out of? Well, they come out of the highest energy, so those are going to come out of the pi 2p star, and so for O2, 2 plus, I would have 8 minus 2 over 2, so I would have 6 over 2, and so I'd have a bond order of 3. Okay, so if I add electrons into an antibonding, the bond order goes down. And if I remove them from an antibonding, then the bond order is going to go up. Just the opposite for bonding orbitals. Okay? That was a hard one. Questions on that one at all? Okay. All right, getting out of the bonding a little bit here. Number 11. Good. Number 12. You guys feeling pretty good balancing? Just a lot of trial and error. Good. Number 13. 13 was D, right? None of those? Is that what it says? Yep. Okay. 14. Okay, so with 14, the key word there is on a microscopic level. Okay, it's probably not a great term to use for atoms because you can't see atoms with a microscope either. But and a really teeny tiny small, they could have said nanoscopic. That would be a better word, nanoscopic. So when we write a reaction, we can either write it in terms of molecules or in terms of moles. So it can mean N2 plus 3H2 goes to 2NH3. That can be a molecule of N2 and 3 molecules of H2 react to give us 2 molecules of NH3. So on a microscopic level, that's what it would mean. We generally use it to mean moles. So we said 1 mole of N2 plus 3 moles of H2 go to 2 moles of NH3. Okay. I put that on the practice because it's just important to know that it can mean either of those 2 things. And it's the reason that we can use the term moles, because it refers to a number of molecules directly. We've never asked something like that on the test. I thought it was a good question for a review, just to remind you of what that reaction notation really means. All right, number 15. Yes, so how many moles of CuO can be produced with 0.450 moles of Cu2O in the following reaction? Okay, so when we're doing these reactions here, this is number 10. So for number 15 here, when we're doing these reactions, remember we're generally going from grams, turning those into moles, and then converting those into moles of something else, and then turning that back into grams. So that's kind of our flow chart there. But I know for my sections, I've told you to watch out on the problem. Really read the problem. Ask, where is it entering that flow, and where is it exiting that flow? Okay, and this problem, we're given moles, and it's asking for moles. So really, we're entering there, and we're exiting there. So we just need to do one calculation. We just need to convert moles of one thing into moles of another. We're not even dealing with grams here because the problem didn't ask us for grams. It just asked us for moles. So we want to take what we're given. We're given 0.450 moles of Cu2O. And we're going to convert that into moles of CuO. Well, if we look at our stoichiometry, we get 4 moles of CuO per 2 moles of Cu2O. Okay, so that's taken directly from the Valence coefficients in the reaction. Okay, and notice that I put the moles of Cu2O on the bottom because we want those to cancel out. And we have CuO up on the top because that's what we want to be left with. So our moles of Cu2O cancel, and so we essentially have 0.450 times 2, which gives us 0.900 moles of CuO. Okay, questions at all on that one? All right. Number 16. Yes. I should just plan on the rest of these being done here. So for 16, how many moles of BCl3 are needed to produce 25 grams of HCl in the following reaction? Okay, so here we are given grams, and we need to exit at moles. So we're entering at a mass, and then exiting at moles. So we're going to have at least 2 calculations to do. We're going to have to turn our grams into moles, and then relate those moles into moles of something else. And then we're done. Okay, so just a 2 calculation one there. It's a good way of looking at it, I think. So we want 25 grams of HCl. Okay, so we want to convert that into moles, so that's times. What do we got there? 1 mole. And if we find the molar mass of HCl, it's 36.45 grams. We just add up the hydrogen and the chlorine. So my grams of HCl are going to cancel. It's going to leave me with moles of HCl. And this comes out to be 0.6859 moles of HCl. Okay, so now I know how many moles of HCl I have, or I want. And what I want to know is how many moles of BCl3 am I going to need to make that many moles of HCl. So for this, we'll use the coefficients for the stoichiometry. So we're going to take this value right here. That's going to be our starting number for our next conversion. So we got 0.6859. That's an 8. Moles of HCl times, and we look at our reaction, and we have 1 mole of BCl3, that's what we're looking for, over 3 moles of HCl. Okay, so now my moles of HCl can cancel, and it leaves me with the moles of what I'm looking for there, and so we end up with 0.229 moles of BCl3. Okay, so that should be B. Yeah. Okay, so again, just think of that flow chart. Grams to moles, moles to moles, moles to grams. Think about where you're entering and where you're exiting. What's the problem giving you, and what is it looking for? All right, 17. Yeah? Okay, I got it. So we need to balance the chemical equation given below, so you can see it's got blanks right in front of it, and determine the moles of iodine that react with 10 grams of aluminum. Okay, so once again, we're given grams of material, and we're asked for moles of the other material. So we're going to need to convert grams into moles for that one material we were given grams for, and then moles into moles of the other material, and then we're done, because that's all it wanted, was moles of that other material. But we've got to get this balanced first. So we want to write our aluminum here plus our I2 going to Al2 I6. Oh, missed an L there. So I got one aluminum here and two over here, so I'm going to need two of those. I got 6 iodines here, and they come in pairs here, so I need 3 of those. So I've got coefficients of 2, 3, and then 1. Okay, so I've got to balance it first, otherwise all the calculations we do are meaningless. Okay, so we just want to do our conversions. We've got 10 grams of aluminum times 1 mole. We use our molar mass of aluminum, so 1 mole per 26.98 grams off the periodic table, and my grams of aluminum cancel, and that leaves me with 0.3706 moles of aluminum. Okay, and so now I want to take moles of aluminum and convert them into moles of I2. So I'm going to take this value right here. I'm going to bring it down for my next conversion. So 0.3706 moles aluminum times, and we look at that balanced reaction, and I would need 3 moles of I2 per 2 moles of aluminum. So now my moles of aluminum cancel, and it leaves me just with moles of I2, and when we work that out, we get 0.556 moles of I2, which is what the problem was asking for. And that answer is A. Questions at all there? Are we doing okay? All right. 18. Yes. So dinitrogen monoxide gas. So here we're given a chemical name, not a formula, but we can work that one out. Decomposes to form nitrogen gas and oxygen gas. How many grams of oxygen are formed when 5 grams of dinitrogen monoxide decomposes? Okay, so the real key here is balancing that reaction. Okay, so this is, which one? 18. Okay, so we got dinitrogen monoxide, so N2O, and that decomposes, which means it's reacting all by itself, just that one, decomposes into nitrogen gas and oxygen gas. Okay, so now we just need to balance that. So my nitrogens are balanced, so that's nice. But I got 2 oxygens over here and only 1 here, so I'm going to need 2 there to balance the oxygens. Now my nitrogens are out of balance, but I can put a 2 here, and that balances my nitrogen, so I've got a 2, and a 1. Okay? I have this one worked out. All right, so we've got 5 grams of dinitrogen monoxide. So got 5 grams times 1 mole per. That's going to be about 44 grams for the N2O. So we get 0.1136 moles of N2O. Okay, and so we want to convert that into moles of oxygen, and so we take that number of moles, we got 0.1136 moles of N2O, and now we use our molar ratios here for the oxygen and the N2O. We get 1 mole of O2 for every 2 moles of N2O, and so that comes out to be 0.0568 moles of O2, because my moles of N2O cancel. And now we take that answer and convert that into grams, and so that's going to be 32 grams per 1 mole for my oxygen. And we get 1.82 grams of O2. So that should be C. Okay, so that one had to go through that flow chart. We entered in grams and we exited the grams. So we had to do grams to moles, moles to moles, moles to grams. But again, these are nothing more than conversions. It's all they are. It's just conversions. Okay, you guys want to see 19? Okay. So for 19, it says when 10 grams of calcium metal is reacted with water, 5 grams of calcium hydroxide is produced. Using the Valence equation, calculate the percent yield for the reaction. Okay, so here we're given a mass of material that we put in, and we have an actual amount of mass that we got out. So we have an actual yield. We're looking for percent yield. Remember, percent yield is equal to our actual yield over our theoretical yield. We have an actual yield, but we don't have a theoretical yield. We don't know how much was supposed to come out. We only know what we actually got out. So we need to use the 10 grams that we put in, 10 grams of calcium we put in, and figure out how much water, or how much calcium hydroxide rather, should have come out. Okay, so we're going to do that part first. So we've got 10 grams of calcium metal times 1 mole, or 40.08 grams. So there we get 0.2495 moles of calcium. Okay, so we're going to take that number of moles of calcium, and we're going to convert that into moles of calcium hydroxide. Now, when we look at our balanced reaction, we see that both calcium and calcium hydroxide have coefficients of 1. So we get 1 mole calcium hydroxide per 1 mole calcium. Moles of calcium cancel, and the 1's kind of cancel, if you want to think of it that way. So we still end up with 0.2495 moles of calcium hydroxide, and now we're going to take that number of moles and convert that into grams, and that's going to tell us how many grams of calcium hydroxide we expected to get out. Okay, and calcium hydroxide is 74.08 grams per 1 mole. So my moles there cancel, and we get 18.48 grams. So that's the amount of calcium hydroxide we expected to get out. We didn't get that much out. Okay, we only got 5 grams out. Okay, so my percent yield is going to equal my actual 5.00 grams over my theoretical 18.48 grams. We multiply that by 100%, and when we do that, we get 27.1%. So we didn't get a whole lot out. Okay, and that is answer what? A. Questions at all on that one? All right. Number 20. 20 is a limiting reactant one. We definitely want one of those. Okay, so for number 20, it says determine theoretical yield of HCl if 60 grams of BCl3 and 37.5 grams of H2 are reacted according to Paul's Valence's reaction. And they gave us a molar mass for some reason in that problem. But we see that we're given two masses of our two reactants. Anytime you see that, you can just assume that you have a limiting reactant problem. Okay? So, first step we want to do, we still want to go grams to moles. We're going to go grams to moles for both of our reactants. And then we're going to take a little side step. We're going to see, okay, of those two molar amounts of our two reactants, which one's going to run out first? And that's our limiting reactant. Once we find our limiting reactant, we take its number of moles and finish out our calculation there. Okay, so we're going to do the BCl3 first, just because. So we have 60 grams of it. And we'll use its molar mass that they gave us, 117.16 grams. So that's going to equal 0.512 moles. And then we're going to do the water. Okay, so that's 37.5 grams. And that's just got a molar mass of about 18. Okay, so that ends up being 2.08 moles. Now we can't just look at the number of moles there and say, oh, well, BCl3 has fewer moles, so it's going to run out first. And the reason we can't do that is because water gets used up 3 times faster than the BCl3. Because the coefficient in front of the BCl3 is a 1, the coefficient in front of the water is a 3. Okay, so what we do to find limiting reactant is we take these number of moles and we divide them by that balancing coefficient. So that comes out to be 0.512. We're going to divide that one by 3 because its coefficient is 3. And that gives us 0.694. Oops, 6. Now, since that 512 here is the lower number, then the species that belongs to that number is my limiting reactant. So BCl3 is in fact my limiting reactant. So we are going to use this number of moles to carry out the rest of our calculation. Okay, so now we've done grams to moles. Now we do a moles to moles calculation. So we take 0.512 moles of BCl3 times 3 moles of HCl, because we're trying to figure out how much HCl we expect to get. And that's per 1 mole of BCl3. So I realized today my CLs look like U's. It's just because my daughter asked me that today. I was helping her with dot structures, and she goes, "Why is that a U?" I go, "That's a CL. It's a chlorine." I guess it does look like a U. It's a CL. So that equals 1.536 moles of HCl. So now I know how many moles of HCl, and I find number of grams. It's hard for me to write way down here on the bottom. I have a lot of support on my hand. So we end up with 56.0 grams of HCl. Okay, so that would be answer C. Are we good at that one? Questions? All right, so that was number 20. 21. So we did that one in class. That was a clicker question, so I'm not going to go through that one. But you do the same thing. You go through, you convert all of those masses into moles, and then you take those moles and divide them by the balancing coefficient. So whichever number is the smallest, that's your limiting reactant. Okay? Pretty much the same as we just did. All right. So 22. It's the definition there. Hopefully you guys are okay with that. 23. Yeah? Did I hear yes? Yes. Okay. You guys, you got to be loud. So we know how many grams of AgNO3 are needed to make 250 milliliters of a solution that is 0.135 mole. So if we look at what we're given here, we're given a volume of a solution and we're given its concentration. What can we figure out from volume and concentration? We can figure out moles. And if we can figure out moles, what can we figure out? We can figure out grams. So that's kind of how we're going to do this one. So we want to take our molarity. See, this is number 23. Right? Yep. So we've got a 0.250 liter solution. That's our 250 milliliters. Is it up there? Okay. Times 0.135 moles per liter. So my liters cancel. So when I calculate that out, I get 0.03375 moles. Okay, so now we know how many moles of silver nitrate we need to make that solution. And now we just want to figure out, well, how many grams is that? So we're going to take those number of moles there. And we're going to convert that into grams. So we're going to use molar mass. Now our moles cancel out, and we get there's a 0 there, sorry. 5.73 grams. So that would be answer D. I'm not done?
Never mind. I'm sorry. I was looking at the wrong one. I just embarrassed myself.
I said, I know I'm not done. I'm only on problem 23. But if you want me to be done, I mean, I'm happy to finish 10 minutes early. Any other questions on that one? Everybody good? I always wonder if I could do stand-up and handle hecklers. I don't know if I could. It's fun teaching class, though. Let's see, so number 24. So 24 is very much the same kind of problem. It's just going back the other way. We're given grams of sodium hydroxide. If we have grams, we can find what? Moles. And so if we know moles and a molarity, what can we find? The volume, and that's all it's asking for. So pretty much the same kind of problem. So I'm not going to go through all the details on that one because it's really kind of the same problem that we just did. So I'm going to cross that out there. If you still can't get it sometime tomorrow, stop in and we'll go over that. Number 25. So 25, I'm not going to go through 25 because I want to ask you a question on that. On the exam, this is just kind of something to be aware of that sometimes you'll run into if you have these kind of calculations. So you can go through and look for the concentration, but here it's looking for, or it gives you the number of milligrams of chloride ion. And the key here is, and this is the tripping point, is that you need to convert, you have to remember that there's 3 moles of chlorine for every mole of the aluminum chloride. So you've got a 3-to-1 ratio in there that you have to take into account. I will not ask you a question like that on the exam. So chances are you got done in by that 3-to-1. But you just take the mass, convert it into moles, take your moles and your volume, you've got your molarity. Okay? And then take into account that 3-to-1 ratio. Okay, how about number 26? Yep. Okay, so for 26, we're just doing a dilution problem here. We're going to take 9 molar H2SO4, and we want to make 0.25 liters of a 3.5 molar H2SO4. So we're going to take 9 molar sulfuric acid and dilute it down to a 3.5 molar sulfuric acid. So we've got to add some water. Now notice that it asks you for milliliters at the end, so it's just something you got to watch out for in your final answer. So let's look at number 26 then. So we can use this equation where M1 V1 is equal to M2 V2. That's our dilution equation. And so we know what our M1 is. So M1 is equal to 9.0 molar. Our V1 is equal to something we don't know. Our M2 is equal to 3.5. And our V2 is equal to 0.25 liters. Okay, so let's plug in everything we know. So we've got 9.0 molar times V1 is going to be equal to 3.5 molar times 0.25 liters. So V1 is going to be equal to 3.5 molar times 0.25 liters over 9.0 molar. Our molarities cancel, and we end up with a V1 of 0.0972 liters. It didn't ask for liters, it asked for milliliters, so we need to convert that into milliliters. So we just use our milliliter to liter, or liter to milliliter conversion, and we get 97.2 milliliters. So we just need to multiply that by 1,000. So the answer is 97 for 2 sig figs. Any questions on that one? Okay. Now let's see. 27. Yeah? Okay, so for 27, we're just looking for the molarity of a solution, molar concentration. That's just molarity. We're given a mass of benzoic acid and the volume of the solution. So we're given a molecular formula for benzoic acid, so we got to find the number of moles there. So we've got 4.79, is that right, grams. I'm just going to write Ba for benzoic acid. If we add up that molar mass, we get 122. Okay, so that comes out to be 0.03296 moles. 926. Okay, so we know the moles of benzoic acid, and now we just need to use molarity. So molarity is equal to moles over the volume in liters. So we're going to put 0.03926 moles over, and we've got a 100 milliliter solution, and so that's going to be 0.100 liters, and so that ends up being 0.3926 molar solution. So 27, so that would be answer B, 392. Technical price would be 393, but they didn't know. Questions on that one? Everybody good? Let's see, 28. Yes. Okay, so for 28, we want to know what is a complete ionic equation for the reaction of aqueous ammonium sulfate with aqueous barium chloride to form solid barium sulfate and aqueous ammonium chloride. Okay, so we can look at our reactants here. So we've got aqueous ammonium sulfate, so that's going to be NH4,2SO4, so you got to know how to make that. That's aqueous, plus aqueous, barium chloride. So barium's a 2+ ion, chlorine's a -1, so that's going to be barium chloride, so that's also aqueous. So I'm just writing out the complete molecular here. We're going to form solid barium sulfate. That's going to be BaSO4
I'm going to write a little S there. And aqueous ammonium chloride, so NH4Cl. So that's all of our players there. We do want to balance it first. So I've got 2 ammoniums here, so I've got to have 2 ammoniums here. That gives me 1 sulfate, 1 sulfate of barium, 2 chlorines, and 2 chlorines. So that's all I needed to do to balance it, was to put that 2 there. Now, let's go ahead, in order to get to our net ionic, because that's what it's looking for. Oh, and it's looking for a complete ionic. Anything that's aqueous, I've got to break apart, and anything that's solid gets kept together. Okay, so we know that these 3 that aren't labeled are aqueous. So this is going to break into 2 NH4 pluses, plus a sulfate with a 2 minus, plus my barium with a 2 plus 2 chlorides with a minus. That's going to go to, now my barium sulfate is a solid, so we keep that intact as a solid, plus that's going to be 2 NH4 pluses and 2 Cl minuses. So all of my aqueuses just break apart there. And so that answer would be D. Questions at all on that one? Getting to the end here. Let's see. 29. Don't worry about 29. That one was a mess. I need to just take that one off of there. So Mercury does something really weird when it's an ion. Mercury 1 forms a diatomic ion. It forms Hg2, 2+. That's Mercury 1's ion in solution. It's weird. It's the only thing that does that. So I wouldn't give you anything like that. I need to take that one off for you to practice. Let's see. How about number 30? Good? Yeah? Okay, so for 30, so we're combining aqueous solutions of barium iodide and K2SO4, and we get a precipitate of BaSO4. Okay, so we don't have the barium, that's in the solid. We don't have the sulfate, that's part of the solid. So we look at the spectator, so those are the ions left in the solution. And so the only other ions we have in there are the potassium and the iodide. So they're your spectators. They're not part of the precipitate, they're part of the solution. Not part of the problem, part of the never. So yeah, K plus and I minus it. Let's see, how about 31? Yes? Okay, so we want to know which combination will form a precipitate. So one of the harder parts on that one is reading that formula there. Okay, so we want to use this table there to see if we're going to form things that are insoluble. So we want to use our belly button rule, which if you're not in my sections, you don't know what a belly button rule is, other than if you don't know the answer to a problem, you just go. No, so the belly button rule, because you've got 2 types of belly buttons. You've got innies and outies. And so when you have precipitation reactions or acid-base reactions, that's what you're combining. You're combining the innies and the outies for the reaction. So for NaCl and C2H3O2, which is acetic acid, so we're going to combine sodium and the acetate. Well, sodium ions don't form precipitates ever with anything. And we're going to combine the H and the Cl. Well, the Cl doesn't form precipitate with H, so that's not going to form any precipitate. For that second one, our outies is going to be the silver and the acetate. Well, acetate is right here. That doesn't form any precipitates. That C2H3O2 is an acetate ion. It doesn't form any precipitates, and there's no exceptions. And then the calcium and the nitrate, Well, the nitrate doesn't form any precipitates, and there's no exceptions. So no precipitate's going to form there. For C, Na and Cl, our outies, are going to get together. And, well, sodium doesn't form precipitates with anything. H and OH are going to form water. Water is not a precipitate unless it's raining and you're in meteorology, not in chemistry. It's not a precipitate in chemistry. This one here, our outies, are going to be the NH4 and the Cl. Well, the ammonium cation, NH4 plus, does not form any precipitates. No exceptions. And then H and OH, once again, are going to form water, not a precipitate. Our last one here, we're going to have sodium and nitrate. Neither of those form precipitates, so, not going to get a precipitate. And then we have iron and hydroxide. Now, most hydroxides are insoluble, but there are some exceptions. But iron is not one of those exceptions, and so it will form a precipitate. Iron and hydroxide. So the answer there is going to be E. That's the only way to go through those, is looking at each reaction, looking at the possible products by comparing the outies and the innies, the outer two ions and the inner two ions, to see what kind of compound we're going to make. Okay? We call that the belly button rule. Let's see, so 32. So we didn't really talk about that in class. I don't know if the other sections did. My guess is not. It wasn't on the slides. So there's 6 strong acids that you need to know. Remember, to be a strong acid, it just means it's a strong electrolyte with acid properties. Okay, so your strong electrolytes, your strong acids, are 3 of your binary acids, HCl, HBr, and HI, and then it's 3 of the oxy acids. Sulfuric acid, H2SO4, nitric acid, HNO3, and perchloric acid, HClO4. Okay, those are the only acids that are strong. Every other acid is weak. Okay? We wouldn't ask you that question on this exam. They do have those acids listed in the chapter, but we didn't really talk about them. We really kind of saved them until 143. Yes, I'm sorry, question.
So we need to know the strong.
Just if it's a metal and a hydroxide, it's strong. But I wouldn't ask you what's the strongest. Let's see. Number 33. Yes. So this is a titration one. So there's different ways that we can work our titrations. We can work them from a mole standpoint, okay, where we calculate the number of moles of our acid using the volume and the molarity, and then use our stoichiometry for the reaction, and then use the number of moles to figure out, or the volume and number of moles in the new volume to figure out what the new molarity is. If you want, if you have 2 acid bases, both that are monoprotic, so your acid's monoprotic, gives away 1 H, and your base is monobasic, which just has a single OH minus, which is the case here. You can use this equation. For my students, you didn't see this because we didn't have the opportunity to, but we can use this one. So molarity of the acid times the volume of the acid is going to equal the molarity of the base times the volume of the base. Only time you can use this is if your acid is monoprotic and your base is monobasic. In other words, it makes 1 OH and it makes 1 H plus. If you have anything in there that's got 2 OHs or 2 H's, it doesn't work. Okay, then you've got to worry about the stoichiometry. You've got to do it the long way. But if you've got just 1 OH and you've got 1 H that comes off, you can do it this way and it's a little bit faster. So molarity of the acid times the volume of the acid is going to equal molarity of the base times the volume of the base. And it looks an awful lot like our dilution equation, and mathematically it's the same, but it has different meaning. Okay, so we can take our molarity for our acid, which we don't know. That's what we're looking for. The volume of the acid. Now here's a case where we can use milliliters, as long as we use milliliters on the other side, which we were given. So molarity of our base 0.250 molar, times the volume of our base, 29.6 milliliters. So we solve for the molarity of our acid here, and we get 0.42 molar. Okay, once again, if you try to do this with something that's dibasic or something that's diprotic, it won't work because you probably have a 1:2 or a 2:1 ratio in stoichiometry. This will not work in that case. But if you got a 1:1, this will work. Okay? Last one, 34. Okay? We're going a little over time, that's all right. As long as there's not anybody waiting outside, which I can't imagine there is. All right, so we're using 6.74 grams of the monoprotic acid KHP. We don't need to know what KHP is because they give us the molecular weight. It's dissolved into water. Samples titrated with a 0.703 molar solution of calcium hydroxide to the equivalence point. What volume of base was used? So here's a case where we got calcium hydroxide. It's dibasic, COOH2. It's got two bases in there, so we can't just do a MAVA equals MBVB one. Okay, so let's look at our acid here. So KHP, that stands for potassium hydrogen phthalate. It actually that's not a chemical formula. It's not a potassium, a hydrogen, and a phosphorus. It's got a big, long, actual chemical formula there. Like I said, we don't care what it is. So we want to figure out how many moles of acid we've got. So we've got 6.74 grams of KHP. And we're going to multiply that by 1 mole per 204.2 grams. So that tells me that I have 3.30 times 10 to the minus 2 moles KHP. I should probably write a chemical reaction up there because we're going to need to use a stoichiometry. So we know that we've got calcium hydroxide, CaOH2, and my KHP, they said, is monoprotic, and that means it just gives off one H+. Well, this gives off two OH minuses. This gives off one H+. So I'm going to need two KHPs to neutralize just one calcium hydroxide. That calcium hydroxide, every mole is spitting out 2 moles of hydroxide. So I'm going to need 2 moles of KHP spitting out 1 moles of H. And so that's going to give me 2 moles of water. And we're going to get a calcium ion. And 2, I'm just going to call them KP minuses for lack of a better term. That's not terribly important that we know what that is. Okay, so we got that many moles of KHP. Now we want to turn that into moles of calcium hydroxide. And so we know that we need 1 mole of calcium hydroxide for every 2 moles of KHP. And again, that's because we've got that 1:2 ratio in our balanced reaction because the KHP is monoprotic, calcium hydroxide is dibasic. And so that's going to give us 0.165, that didn't come out right, moles of calcium hydroxide. Now I can take my moles of calcium hydroxide and convert that into a volume using molarity. So that's 1 liter because it's 0.703 molar. So I got 0.703 moles of calcium hydroxide for every 1 liter of solution. And so this comes out to be 0.0235 liters, which ends up being 23.5 milliliters. And so that would be answer D. So that was 34 problems. Took us a little over an hour. Your exam tomorrow has 26 problems, so it's got a lot fewer problems here. All right. Well, hopefully that helped. I will get this posted onto YouTube as soon as I can. Otherwise, good luck tomorrow.